The graph below shows the result of the titration of a 25 milliliter sample of a 0.1 molarity solution of a weak acid HA with a strong base 0.1 molarity NaOH. Describe two features of the graph above that identify HA as a weak acid. One way to identify that this is a weak acid is that its initial pH value starts at 3. Most strong acids pH values start at 1. So since the pH is greater than 1, it shows that this is a weak acid. And another way you can tell is that the equivalence point for this is above 7, which indicates that at the equivalence point and on, the acid has all run out and that what's remaining is base, so that indicates that this was a weak acid. One method by which the value of the acid association constant for HA can be determined using the graph above is that where the half equivalence point, at the half equivalence point for a weak acid strong base, the pH will equal the pKa, and since we know the pH based on where the half equivalence point is, we can find pKa by 10 to the negative pH. On the graph above, sketch the titration curve that would result in 25 milliliters of a 0.1 molarity solution of HCl, where used instead of 0.1 molarity of HA. So the black line is the titration that they showed, and the pink line represents the titration curve that would result if 25 milliliters of 0.1 molarity of HCl were used instead. And you can tell because HCl is a strong acid, which means its pH would be equal to 1 for its initial value, so that already indicates a strong acid because, like was said earlier, the weak acid was greater than 1, so since this is equal to 1, you know that a strong acid was used, and you know 0.1 molarity solution is a very strong amount of HCl. A 25 milliliter sample of 0.1 molarity of HA is titrated with 0.20 molarity NaOH. What volume of base must be added to reach the equivalence point? So what I did to solve for this is I took 25 milliliters times the molarity of HA, which was 0.1, to find the millimoles, and I got 2.5 millimoles of HA. So since HA is equal to OH, 2.5 millimoles is equal to 2.5 millimoles of OH minus. So I put the millimoles over liters to find the milliliters, because molarity is moles over liter. In this case, it would be molarity is equal to millimoles over milliliters. So 2.5 over 0.2 equals 13 milliliters. The pH at the equivalence point for this titration is slightly higher than the pH at the equivalence point in the titration using 0.1 molarity NaOH. Explain. So with the titration using 0.1, its total volume is 50 milliliters. With using the 0.2 molarity of NaOH, for the equivalence point, the total volume is about 37.5. And if you were to plug it into your calculator to find millimoles, 37.5 times 0.2 is 7.5, and 50 times 0.1 is 5. So you can already tell that 7.5 is greater than 5. So with those millimoles and putting it over the volume, which is the molarity of millimoles over milliliters, it'll give you a higher concentration than using 0.1. So since it's a larger concentration of A minus, and the Henderson-Hasselbalch equation is the pH equal to pKa plus log of A minus concentration over the HA concentration. If you have a larger number on top, it'll result in a larger number in general than if you were to have a larger number on the bottom. So therefore, with the smaller volume with a greater amount of moles, the pH is slightly higher.